Hi all, my name is Persoons. I'm an assistant professor in mechanical engineering in Trinity, and I'd like to give you some details on what mechanical and manufacturing engineering is all about, um, why you might want to do it, and why I love it, why you might love it as well. Um, so key questions for this presentation is, first of all, what is mechanical engineering? What does it entail? And also, what does a mechanical engineer actually do on a day-to-day basis? So you can see a couple of examples here, and we'll talk through some of these in the next few slides. So first of all, what is mechanical engineering? If you go to the definition, it's a diverse profession that lies at the crossroads of all engineering disciplines. It's the broadest of all engineering disciplines, in fact, and it's proven to be one of the most popular options for all of the engineering streams in recent years. So yeah, it's a professional engineering discipline. You can see some examples here of future car designs, aerial vehicles, robotics, etc. Key concepts include, a host of topics as listed here, so mechanics, kinematics, thermodynamics, etc. All the way down the list, it's one of the disciplines that has probably the broadest range of topics that you can cover, and that you actually need to cover in order to be a good mechanical engineer. So it's again, it's one of the broadest disciplines. It allows you to, specialize in certain areas, of course, but you still have to have this really broad range of background knowledge in all of these. So our education is, really reflects this, right? You have a variety of choices through the years. More choices, obviously, the further you go. So in years 4 and 5, you have a lot of choice. And that's where you can really then specialize in one or a few of these topics, and that tends to work pretty well for our students. So you can see some examples here, some animations of research results. On the left, what you see here is a so-called thermal interface material that's being compressed down. In the middle, you see actually one of my students' results, which are these are two synthetic jets that are pulsing, and these are used for either for cooling of electronics or for flow control, for flow separation control, for instance, for aircraft. And then on the right-hand side, you see a simulation of a bubble, a rising bubble in a pool of liquids that's bouncing off the ceiling. And in this configuration here was a research that was a collaboration with Nokia when they were looking at enhancing the cooling in solar PV panels. But you can see a very wide range of topics that would be of interest to mechanical engineers there, from car design, trains, aircrafts and rockets, all the way down to biomechanical devices, robotics, computers, phones, etc. As it says there, pretty much everything. So one of the areas would be, climate change, the environment, energy use, and all of that. You can see some examples here. One of the things that I work on a lot is data centers and electronics cooling in general, and how we can reduce the energy use in those systems. Another area would be acoustic noise, for instance, environmental noise, where we do a lot of work on aircraft noise generation and sort of control of that noise to try and improve the noise emission from those systems. Also wind turbines, for instance, as you can see there. And we also have some staff who are involved in a spin-out company that do noise mapping in urban areas. And you can see an example there of sort of a noise intensity map in the Dublin area. So obviously higher noise closer to the roads, less noise in less populated areas. Power generation obviously is a very big deal. So what you see here is sort of the dark image of composite image of the Earth with the illuminated centers. Renewable energy is obviously a hot topic these days. So whether it's wind turbines offshore or onshore, the image in the bottom right here is a tidal turbine. Wave energy, so all of these things are things that mechanical engineers would work on. As I said, electronics cooling is an often overlooked problem. Certainly a particular challenge for Ireland as well. If you think about the total electricity consumption in Ireland, currently in 2020, about 15% of the total electricity consumption is being used by data centers. So, if you think about all of these sort of, Googles, Facebooks, all of that, all of those facilities, if you combine all of those, that's about 15% of the total electricity consumption. So that's a huge fraction, right? And the thing is, this is really the only sector that's rapidly growing as a function of time. So EirGrid is expecting these data centers to consume anywhere between 25 to 30% of the total national electricity consumption in 10 years, so by 2030. And so this is obviously a big concern for policymakers, and it means that there's a strong need for people like ourselves, like mechanical engineers, to go in and to help reduce that energy footprint. And one of the key things in data centers is heat, is the problem of how do you cool these things in the most efficient way. It turns out it's about 30% or so of the overall energy consumption is being used by the cooling system. So even if you can only make small changes in improvements in the cooling system efficiency, that's still a big impact in terms of climate, in terms of carbon emissions and cost reductions as well, obviously. So here's some other examples. I probably won't go into the details here, but there's not just data centers, but there's other topics such as telecommunications, etc., where cooling is very important. Novel aircraft design. We don't have a sort of a dedicated aeronautics department in Trinity, but even within mechanical engineering, there's several people who do very advanced research on novel aircraft designs, whether it's sort of the design of these new counter-rotating rotors that you see here under a test in a wind tunnel, or, as I said before, the sort of noise generation aspects. There's a lot of work been done on that. What you see here is let's play this video here. Applications of robotics and mechatronics. Doesn't really matter what you're seeing here, but it's basically just a robot arm scanning a certain pattern with a sensor attached. This is actually measuring the radiation coming off a device that's mounted here. Bio-inspired design. We have several people working on these things, so taking inspiration from nature basically to enhance engineering designs. This is a nice example here, starting from an insect wing to look at the sort of the strength of these designs. Here's one of my examples from a former PhD student looking at the sort of analogy between mass transfer in corals, deep sea corals, and heat sinks, again, heat sinks for electronics cooling. Some examples from manufacturing production processes. Everything really from large scales to micro and nano scales is what we do. Metamaterials, 3D printing, all sorts of things. We have, a lot of equipment in the department, but we also work with other more advanced sort of microscopy centers, for instance, where they have really high quality microscopes to be able to characterize these, new materials that are being produced. Here's another example of some complex device design. Materials as well. So whether it's these sort of new shark skin like bio-inspired materials, Bone as well. Now I should say that biomechanics or bioengineering is a separate stream to mechanical and manufacturing engineering. We're housed in the same departments, the Department of Mechanical Manufacturing and Biomedical Engineering, but they are two separate streams. So if you want to specialize in bioengineering, there's a separate stream for that. Mechanical is somewhat broader than just bio itself. Here's an example, again, related to electronics cooling, where you have these diamonds impregnated copper layers that are used for thermal interface materials. Something you may not expect, forensics engineering as well. So one of our professors is an expert who's often called upon by insurance companies, for instance, to investigate accidents or failures of certain devices. And then you have to go into the field and sort of assess, okay, why has a certain fracture happened, for instance, and kind of apply your knowledge to these problems. Some aspects, of course, of biomechanics come into play as well. So what is pedestrian safety, for instance, or vehicle safety. Some fun stuff in space technology, as you can see here. So we have a couple of people who are regularly doing these parabolic flights, for instance, to study the effects of microgravity on some research applications. You can see actually two of our professors here. This is Seamus O'Shaughnessy over here. This is Tony Robinson in the foreground on one of these parabolic flights where they're testing two-phase cooling of, there's a test apparatus over here where which is running in the background basically as the parabolic flight occurs. And then while you're in microgravity, obviously the physics of boiling would change, and they're recording as they go basically, and these results would then be analyzed later on and published in a paper for further use. There's also a number of us who are engaged in sustainable development. Seamus O'Shaughnessy, for instance, is one of them. So there's a lot of work being done sort of in developed countries, for instance, in developing countries, sorry, for instance, with decentralized power generation or recuperating energy from thermal sources, like from cooking stoves over here, to people designing robots to interact with people with disabilities, for instance, or the elderly, to walking frames. As for me, so what I do, my background, so I did my undergrad and my PhD in KU Leuven in Belgium. I joined Trinity in 2006 as a postdoc, and I worked here for some time, moved to Purdue for some years, and then back to Trinity as assistant professor in 2013. So I have a fairly long history, even though I didn't do my undergrad in Trinity. So I know Trinity quite well. I'm now the stream director for mechanical engineering, which is why I'm doing this talk. In terms of teaching, what I do now for teaching is mainly heat transfer and computer-aided design. But I've been involved in many other things like solid mechanics, fluid mechanics, numerical methods, for instance. You can see a few examples of what some of my students have produced as part of these courses over here. In terms of research, so once you get to your 5th year, you would also be doing a research project, which is 30 credits, so it's half of the credits of the whole year. You're then assigned a supervisor, and so on average, each of us would do something like 4 to 6 masters students per year. In addition to that, I also have, at the moment at least, something like 7 PhD students, 3 postdocs. So that's roughly the typical size of my team. What we do, as I said before, is mainly electronics cooling, and we use unsteady flows, oscillating flows, for instance, or plasma actuation to control where flows go in terms of electronics cooling. So, and you can do that on a large scale. We talk about sort of a whole data center facility, or it can be on the micro scale when you talk about the liquid cooling of an individual CPU, for instance, and all the scales in between that. And so sometimes, some of these master students, you can see two of them over here in this picture where we were doing tests in a local data center in Dublin. Other stuff involves, so, a lot of my research again revolves around data centers and how can you recuperate heat from the system. So at the moment, all of this electricity consumption is transformed into heat, dumped in the atmosphere and lost for any further use. But if you were to redesign the cooling system in a smarter way, and that's the goal of my team basically, is how do you design it in such a way that you can recuperate the waste heat from the system at a high enough quality that you can actually do something with it. So whether it's for residential heating, for instance, or for other conversion to other energy streams like cooling or actual electricity generation, that's sort of the common thread in all of my research. So you can see a couple of examples there and sort of partner companies that were involved in this research. So you'll often find in mechanical engineering that although we do fundamental research, we tend to work very closely with companies, both local companies, Glendimplex, Airgrid, SSE, ESB, for instance, but also international companies that may or may not have a base in Ireland. So Nokia has a base here, GE does not, for instance, General Electric. But yeah, so we're pretty good in terms of getting collaboration with companies. And that's to the benefit of our students, of course, because if you're doing a project in collaboration with a PI who has a link with a company like Intel, for instance, it's sort of a natural way then to expand your contact network with that company. And if you like the research and they like what you're doing, there's a good synergy then to perhaps end up in a job in one of these companies. Okay, there's probably too much information here, so I'm not going to go into all the details, but just again to indicate the sort of breadth and scope of the wide scope of a typical mechanical engineer. So even though most of my research is on electronics cooling, I'm also involved in SFI funded research centers on pharmaceutical development, for instance. So SSPC is this center. My activity there is focused on drug dissolution modeling. So using the analogy between heat transfer and mass transfer. So drug dissolution is typically of course something where mass transfer is very important. But using similar principles, you can use the analogy between heat and mass transfer to better understand what's happening in one system if you understand what's happening in the other. So yeah, so even though you may not expect a mechanical engineer to know something about drug dissolution, that's not so uncommon to see. In terms of daily activities, what I would do is, we build test facilities in the Parsons building in Trinity in our departments to verify and validate computer simulations. So computer simulations are nice and they give you nice colorful graphs, but that's not the end of it. We have to prove that these things are correct. So we basically build lab scale test facilities where we can do tests either on full scale systems where we just use air cooled servers, for instance, and measure flow fields in those, or we use representative models in for instance, in liquid flow test facilities where we can get better quality results. So you can see some examples of that over here. So you have to be versatile in, it's not just being a mechanical engineer, it's having some understanding of optics in this case, because a lot of these velocity measurement techniques are optical. So, there's aspects of lasers involved, there's lighting, there's cameras. So, a lot of us working in this area are sort of amateur photographers as well, because a lot of our work involves high-speed photography and and video recordings. So, it's not just, I think if you take anything away from this presentation, is that a mechanical engineer is not just someone who's working in a mechanical workshop and that's it, right? Or is just designing something in CAD and doesn't care about anything else. You have to have sort of a broad range of interests, I think, to be a good mechanical engineer. And here's just an overview of some of the companies that I would be working with. And of course, this is just my team. There's other teams as well. So just to give you a sense of how many companies and institutions that I will be interacting with on a daily basis. And so in terms of industrial sectors that you might end up in as a mechanical engineer, here's just an overview of that. This is by no means exhaustive. Mechanical engineers tend to end up in the most varied fields, right? So not strictly in engineering even. A lot of my friends, for instance, that I graduated with ended up in banks or insurance companies. So yeah, there's a need for this kind of expertise in a very wide range of fields. So again, it's just some examples of where some of our students tend to end up in. And then in summary, so mechanical engineering, it's a 5-year degree program, right? So the first 2 years are common, which is good because you get exposed to all different aspects of engineering, and it gives you time to really understand what it is that you want to do. If you're asked to make a choice in year 1 or 2, I think people tend to maybe sometimes make the wrong choice. Whereas if you have those 2 years to interact with the lecturers from mechanical engineering as well as from civil and electronic, etc., I think you get a better sense of what it is that these different streams are all about. So in year 3, you make your choice, and if you decide to go with mechanical engineering, you still have a pretty sort of solid block of modules that you're supposed to do. There is some choice, but not that much. But once you get into year 4 and 5, you have a lot more choice than to specialize in different areas, like for instance thermal fluids, mechanics, etc. And as I said before, bioengineering is a separate stream, so there'll be a separate presentation for bioengineering. But we're housed in the same department, so we're all housed in the Department of Mechanical Manufacturing and Biomedical Engineering. Okay, that's it from me. Thanks very much for your attention.